Hey guys, this is 7.6 part 2. Before we get started on the new material, I want to kind of go over what we learned in the last video. So we learned about row operations and how you can add and subtract rows. You can multiply a row by a constant, and you can also switch rows out in a matrix. We also learned that this form of a matrix here is called row echelon form. You've got the main diagonal having all ones and then zeros below that. Then we went through a few examples where we solved equations by first getting the matrix into row echelon form and then using substitution to solve for a variable. We did that with two equations in the last video. Today, the first thing we're going to do is three equations with three variables. So we're going to solve this system of three equations with three variables using Gaussian elimination. So first, we're going to put this matrix into, put this system into an augmented matrix. So I've got 1, 3, 2, 1, 2, 1, negative 1, 2, 1, 1, 1, 2. All right, remember the first thing you need to do is get a 1 in the first row, first column. Well, this one already has a 1 there. Right here, we've already got a 1, so perfect. Now the next thing you want to do is get zeros below that. So everything below that 1 needs to be a 0. So I'm going to do row 2 minus 2 of row 1. That way, that 2 will become a 0. And then I'm going to do row 3 minus row 1. Since both of them are 1s, if I subtract them, that first entry in row 3 will become a 0. Okay, let's change that. So first row is not changing. Second row is going to subtract 2 of row 1 from that. So 2 minus 2 gives me 0. 1 minus 6 gives me negative 5. Negative 1 minus 4 gives me negative 5. 2 minus 2 gives me 0. Okay, then we're going to do row 3 minus row 1. So 1 minus 1 is 0. 1 minus 3 is negative 2. 1 minus 2 is negative 1. 2 minus 1 is 1. Perfect. So now we have 1 in the first row, first column, and zeros below that. Now we're going to move to second row, second column, making this negative 5 into a 1. That's the next thing you want to do. So I'm going to do that by multiplying that row by negative 1/5. So I'm going to do row 2 times negative 1/5. That will make that negative 5 become a 1. So 1, 3, 2, 1, 0, 1, 1, 0. Didn't change row 3. Perfect. The next thing you want to do is get a 0 below that. So getting a 0 below that 1, I'm going to do row 3 plus 2 of row 2, because negative 2 plus 2 will give me 0. So 1, 3, 2, 1, 0, 1, 1, 0, not changing either of those first two rows. Now row 3 plus 2 of row 2. Row 3, so 0 plus 0 gives me 0. Negative 2 plus 2 gives me 0. Negative 1 plus 2 gives me 1. And 1 plus 0 gives me 1. All right. Now, the next thing that you would want to do is get a 1 in that third row, third column. But that actually already has a 1 in it, so we don't need to do anything else. So now, what you have, if you look at this part right here, remember this is x, y, z equals your constant. You have, you actually have z equals 1. That's what that tells you. So now that I know z equals 1, I can substitute that back in to solve for other variables. Let's actually write all three of these equations out, just kind of changing this back into a system of equations instead of a matrix. So I've got x plus 3y plus 2z equals 1. I've got y plus z equals 0. And I've also got z equals 1. And so now what you can do is you can work your way back up this system of equations to solve for each variable. I already know z equals 1, so now I'm going to take that 1 and plug it in for z in the second equation. So I'll have y plus 1 equals 0, which means y equals negative 1. Okay, now I'm going to take both of those, the y and the z, and plug them into that first equation and solve for x. So I'll have x plus 3 times y, which is negative 1, plus 2 times z, which is 1, equals 1. X minus 3 plus 2 equals 1. X minus 1 equals 1. X equals 2. So just did some substitution there to solve for our variables. So writing my answer as an ordered triple, I've got 2, negative 1, and positive 1. So not much more challenging with 3 equations and 3 variables. Now, remember that this form that we have here is called echelon form. Row, echelon, form. There's actually another form that you may have heard of before called row reduced echelon form. And what that actually does is not only do you get these 1s in this diagonal, but you also have 0s above. So you have 1s in the diagonal, you have 0s below, and 0s above. So we would have to keep going to get it in a row echelon form. The cool thing about row echelon form is that once you have that, where you have only 1s in the diagonal and 0s above and below those 1s, these numbers in the far right column are your solutions. Those numbers in the far right column are your solutions. So actually what I'm going to do is I'm going to show you that. I'm going to show you that process. So I'm going to just sneak out another piece of paper here, write down that matrix, and show you how to change that to row reduced echelon form. All right, so here's the matrix we left off on with it in row echelon form. So if I wanted to keep going and get this in row reduced echelon form, I would want to get rid of that 3 and make it a 0. I need to make this 3 into a 0. So I would just do row 1 minus 3 of row 2. Okay, so that's going to give me 1 0, -1, 2 minus 3, and 1. Now I also need zeros. Oops, sorry, that was a 0. I need zeros above this third row, third column 1. So I need zeros here because I only want 1s to be in this main diagonal. So to get rid of those two 1s, the -1 and the 1, I'm going to use row 3. So I'm going to do row 1 plus row 3, and that will get rid of that 1 there. Now notice that you can't add row 2 to that. You cannot add row 1 plus row 2 to get rid of that -1 because it would give you a 1 in the second column. You would have 0 plus 1 here. And because we need that to stay 0, you're just going to use the third row, which has zeros in the first two columns. All right. And then to get rid of the 1 in the second row, we'll do row 2 minus row 1. Oh, sorry, row 3. Row 2 minus row 3. We'll get rid of that one. Okay, so first row is going to have plus row 3. So 1 plus 0, 0 plus 0, -1 plus 1, 1 plus 1. Now our row 2 minus row 3, for row 2, 0 minus 0, 1 minus 0, 1 minus 1, 0 minus 1. Row 3 we are not changing. All right, so just with those few steps, we were able to get this in what's called row reduced. Echelon form. And so this is row reduced echelon form because you have that main diagonal being all 1s and everything above and below that as zeros. And so remember, that is your equal sign there. This is x, y, z equals a constant, some number. And so this first row actually says x equals 2. The second row actually says y equals -1. And the third row actually says z equals 1. And so that's what's nice about row reduced echelon form, is that your answers are all in that final column there. You can do that with a system of 2 equations, 3 equations, 4 equations, any number of equations. You can get it in row reduced echelon form, and your solution is there in the far right column. Okay, now let's look at some special systems. We're going to use the Gauss-Jordan method, which is just another name for Gaussian elimination. All right, so first writing this matrix, this system in matrix form: 1, 1, 2, 2, 2, 5. All right, first thing we need is a 1 in the first row, first column. We already have that here. So let's move to making this 2 into a 0. Anything below your 1s needs to become a 0. So to do that, I'm going to do row 2 minus 2 of row 1. All right, so subtracting 2 of row 1 left me with that. Now notice that this second row, second column became a 0. Normally, we need to make that into a 1, right? There's really no way for me to change that into a 1 now, other than adding row 1 back to that, but then that would give me a 1 here. So that's just not gonna work for us. And so let's think about what this actually says. Remember, this is x, y equals a constant. So this is 0x plus 0y equals 1. Well, 0x plus 0y is 0. 0 equals 1. Well, that is not true. So think back to when we were just solving systems of equations. If I ended up with something that was not true, like 0 equals 1, I would say there's no solution. So that's the case here. So basically, if you get all of your variables, the coefficients become 0, so all of your variables go away in one of your equations, that is going to be either no solution or infinitely many solutions. In this case, because it was 0 equals 1, that's going to be no solution because that is not true. Okay, so no solution on this one. This is a inconsistent system. All right, number 5. Let's write this one in matrix form. Now remember from when we solved systems of 3 equations with 3 variables by hand without using matrices, if we had fewer equations than we have variables, aka we have 2 equations but 3 variables, this is going to be dependent. So let's see how that works out using matrices. So I'm going to try to put this in in row echelon form as much as I can. So first, actually, I'm just going to switch these two because then I'll have a 1, first row, first column. So I'm going to do row 1 switched with row 2. Gives me 1, -2, -2, 8, 2, -5, 3, 1. Just switching those out. Okay, now I need to get rid of that 2 below the 1. Need to make this into a 0. So I'm going to do row 2 minus 2 of row 1. Zero. -5 minus 2 times -2. 2 times -2 times -2 gives me 4, so that becomes -5 plus 4, which is -1. 3 minus 2 times -2 gives me 7. 1 minus 2 times 8 gives me -15. All right, now we also need second row, second column to become a positive 1. So I'm going to multiply that row by -1. So I'm going to do row 2 times -1. So negative row 2. So I've got 1, -2, -2, 8. Now this becomes 0, 1, -7, +15. All right, that's as far as you can go for row echelon form on this one because there's no row below that to continue going with. So this one gives us, let's write out our system now. In the first row, we have x minus 2y minus 2z equals 8. In the second row, we have y minus 7z equals 15. Okay, so since this one we weren't able to get any further than that, we weren't able to actually solve for a variable, and because you have more variables than you have equations, you're not going to be able to get x comma y comma z all numbers. You're going to have a variable still involved like we did in our previous section, 7.2. So what I'm going to do is I'm going to solve for y right here in the second equation. I'm going to add the 7z over. So y equals 7z plus 15. That's as good as I can do for solving for y. Now I'm going to also get x in terms of z. To do that, I'm going to plug this in for y in the first equation. So that is x minus 2 times y, which is 7z plus 15 minus 2z equals 8. Okay, so I'm getting x in terms of z. So x minus 14z minus 30 minus 2z equals 8. Combining like terms, I have x minus 16z, adding the 30 over, 38. Now to get x by itself, I'm just going to add the 16z over. Okay, so now I have x equals 16z plus 38, y equals 7z plus 15, and z is just going to equal z. So let's write our answer. So our solution to this dependent system of equations. So in this case, I'm writing my solution as everything depends on z, right? X depends on what z is. X is going to be 16 times z plus 38. Y is going to be 7z plus 15. And z is just going to be z. There you go. That's as good as you can do for that one. All right, that's it for part 2 of 7.6. We'll do part 3 and finish these notes off.